Welcome back to another installment of our OMFIT tutorials. Today we're going to have Brian Grissom talk to us about the GYRO module, which can run both GYRO and CGYRO, and things he's been doing with it.
Absolutely. Okay, thank you, Sterling, for the kind introduction. Someone offsite needs to mute, I believe. Okay. All right, so thanks everyone for joining us. I'm going to walk through how to use the code that's called GYRO. It's a fairly popular and widely used gyrokinetic code for looking at turbulent transport in tokamaks. So this is going to be a tutorial for how to use the OMFIT GYRO module and also the GYRO scan module. Now these are very comprehensive simulations of plasmas. And so we do not have time to go through every element of what GYRO is capable of computing and how to look at its output. But we're going to go over what we call linear stability analysis and then give an example of what a nonlinear simulation would look like. So a prerequisite to this tutorial is a basic understanding of what OMFIT and GYRO are and how they're generally used. You probably have seen some of the previous examples of how to browse the OMFIT interface, so we're not going to cover all of that. This is also not a tutorial on gyrokinetic theory or numerically computing a solution to the gyrokinetic equation. This is a tutorial for GYRO to answer the following two questions, essentially. What are the linearly unstable turbulent modes in a given set of plasma profiles or given set of conditions? And what are the nonlinear turbulent transport fluxes that those instabilities would produce? That would then be compared to, for example, a power balance calculation. So a complete treatment is beyond the scope of this tutorial, so we're just going to go over the basics for how to use the tool. I'll remind people that there is an online Google Doc that is the OMFIT GYRO and GYRO scan tutorial that provides a description. You can see it's fairly complete in the introduction and a tutorial. A number of the elements in this tutorial I'll be demonstrating here. So we're going to start off with importing the GYRO module. And the GYRO code is an executable that lives at whatever institution you're running OMFIT. It could live on your laptop, or it could live on a remote server. For this example, I'm running OMFIT at the Princeton Plasma Physics Laboratory, what we call the PPPL computing cluster. So I've started OMFIT here, and you can see the workspace, and I'm going to import the GYRO module. It's called GYRO GA code. So we can just type GYRO, and you see there's a number of options. There's GYRO with a long description down here, including citations and references. There's also the GYRO scan code. But we'll start with doing GYRO. So we're going to load this module then into our workspace. And we start the modules by double-clicking. Here, a double tap will open the main graphical interface for this module. What this graphical interface really does is drive the underlying elements here, such as scripts and plots, and then the GUIs themselves are all down here. There's a number of library functions that come with GYRO, for example, parsing the output files and things like that for whether or not it's converged, and templates and demos. But for this example, we're just going to act as if we're going to use the graphical interface. So what you're first presented with here is the getting started page of GYRO, where for any simulation, we can give it a name called sim1, which is very similar to a directory. You'll see in a moment how it's important to name the simulations to organize the output of the code. You have, this is called GYRO, but GYRO and CGYRO, which is a newer version of GYRO, or essentially a new code that has a different collision operator, is also available. So one can just swap between GYRO and CGYRO, and this OMFIT module is intelligent enough to know the difference between the two in terms of what the input parameters are and what the settings are. So for this example, we're going to run GYRO, and the mode that you run GYRO in is either you can look at an experimental set of conditions, which we had looked at previously in, for example, the TGYRO tutorial that was a couple of weeks ago. You can run off just an input file for doing theoretical cases where you determine the plasma profiles and parameters. This is also for running regression tests. Or you can load an existing simulation. For example, if you ran a simulation from the command line in some directory, you can load that in and plot it against another simulation you just executed here. So it's fully featured in that sense. For this example, I'm going to be looking at what we call a regression test. It's one of the cases that GYRO produces itself as a test to make sure that the code is functioning correctly. And this regression test happens to be what we call the GA standard case. It's a ITG-dominated, strongly driven set of plasma conditions. And so you can either select an input gyro file here, or you can set up regression test. And so that's what we're going to do. We're going to set up a regression test. And some of the options that we have here is Rego1 and Rego2, or NL01, which is a nonlinear case. For this example, we're just going to run regression case 1. So when I click this button, as you will see, what OMFIT does is it actually goes to the command line and tells GYRO to generate regression test Rego1. And then it loads that input file back into OMFIT. You saw that it was very quick. And what happens is now you have this tab that's called input.gyro. Input.gyro is the master file that has all the settings, the radial position, the time stepping, what wave number you're choosing, what resolution and physics you're including in the simulations. To show where that lives, if I browse in the tree here, I go down here and I go to GYRO GA code, go to inputs and input.gyro. And you can see here that this is a file. It's called input.gyro. And I can browse it like any other entry in the OMFIT tree. It has a list of variables that are floats or integers. I can also always hit spacebar, and it'll pop up here in Emacs, the input gyro file. And so you can look at all the different variables. This is a commented input nameless file. OMFIT imports all the Python classes that come with gyro. So this is all essentially native to OMFIT. I can close this here for a second. I can just use my arrow keys to expand or reduce these drop-down lists.
So how would you get that gyro? We have like experimental data.
I'll cover that in a little bit.
Okay.
If we do an experimental case, what we've done in gyro here is we've given the users a series of templates. And so under templates and gyro, there's a list here that is like a linear gyrokinetic ion, adiabatic electron, electrostatic pure plasma template. Or there's a number of different examples here. We have some examples here that are a linear D through D ion scale simulation that has carbon already as a defined species. One of them is pure plasma, and one of them is with impurities. One of them is ion scales, one of them is electron scales. There's also nonlinear templates here. And so I'll get to that in a second. But if I were to say I'm going to run profiles gen for an experimental case, after you set up your profiles, it'll say, what template do you want to use? And then you just select it and load it in. All right, so some of the commonly changed variables are supported in the graphical interface, but we haven't spent our time making a graphical interface for every possible gyro variable, just the ones that are commonly changed. And this can be expanded in the future, but these are the ones that are normal. So what we have here is we have the radius, the radial coordinate here. When you're running a theoretical case, the only option is radius. But when you have an experimental profile, you can say, I want to do my simulation at rho or psi normal, which are two other common experimental coordinates. And it will translate that to the gyro variable radius.
So what is the units of this radius?
This is R over A. You can always look in the gyro online documentation to look up the meaning of the various variables. The next thing you have here is the time step, where the time step is normally in terms of CS over A, which is the gyrokinetic time step in units of CS over A. So here I'm going to be doing a time step of, for example, 0.1 CS over A is how I'm going to advance the gyrokinetic equation. If you don't know what number to use, you can also use a CFL multiplier, and we can calculate what the time step is for a given CFL condition if you want.
What is CFL?
Courant, Friedrich-Levy numerical integration error. So in computational fluid dynamics, you cannot have a wave that propagates faster than the time step of the simulation because it can't capture it. So that number needs to be less than 1 in an explicit time advance for the linear inflection equation. You can set the time here, so the maximum time. And if you use a decimal, that's the precision to which gyro will test for convergence. So if it gets down to a 10 to the minus 3 on the frequency, it'll stop. It'll exit before the end. We'll say it's done. And then there's the output style. Either you can output every number of time steps, or you can output every number of A over CS. So if you want to just put out every logical unit in time, that would be 1. So here, if I say I'm going to put n is 1, so every A over CS, I will output the result of gyro, the evolution of the eigenmode. It says down here it'll produce 100 output files, or output times for this. Then you move on and you have what we call the box, or the radial domain. This is a linear run, so you simply specify the wave number, k theta rho s, that you want to run. And that variable is called L underscore y, is the variable in gyro. So if you go to inputs, input.gyro, you see down here is ly is 0.3. If I change it in the GUI, you see it just changes it down here. And it's just a convenience. And then in terms of resolution, we have what we call an expert mode, true or false, is where you can set all the individual resolutions of the gyro orbit grid, the radial grid, all these things. Or there's a couple of radial resolution and poloidal resolution numbers, where if you use one number, then multiple variables will be set based on that. This can all be looked at on the online gyro documentation. Then in terms of physics, there are things like the number of fields you want to evolve. It's electrostatic or electromagnetic. And then in terms of outputs, what do you want to plot? Here we're just going to plot the U moment and the number of points in theta that you want to plot. So before you run any gyro simulation, you always want to, what they call, sanity check your input file. You can run gyro and it'll say gyro-t from the command line. Say test gyro. Compute a bunch of things based on my inputs to make sure that my simulation will function properly. And so that's what we're going to do here. We're going to test gyro, and it provides this button here. And so when I click on test gyro, what OMFIT does here is it goes to it puts the input file on disk on a remote host. It executes the command gyro-t, which produces a bunch of text output files. It gathers those output files from the remote host and pulls it back into gyro so you can view it. And in the command box over here, you see that it printed out a whole bunch of text. You can see it's this long description of what your simulation is. If you ever have a problem with the simulation, Jeff Candy will ask, send me out.gyro.run to let me see what your simulation looked like. And so after we run this test, we have these various new buttons that show up here. It's called view out.gyro.run. And you can see here what are the settings for our simulation. It's an initial value, periodic, flat profiles, S alpha geometry, adiabatic electrons, etc. And if you scroll down here, you can see much more information about what the numerical parameters are in terms of the resolution, in terms of the radial and poloidal wave number. And then it'll say at the end, it'll say test complete.
What will it say if it fails?
It'll be a bunch of warnings. It'll say, warning, gyro operator bandwidth is too small. It needs to be bigger than some number. But you can always click this button here that says check out.gyro.run, where I parse that file for problems. And for this example, it just says status test complete, because that's all that I did is run a test. Now, when you run a simulation, gyro will put information at the bottom of that file that says, unconverged, converged, interrupted, numerical blow-up, etc., various issues. You can also view something here that's called view out.gyro.efficiency, and this is the number of MPI cores that you could use to run this case. So I could run one MPI process with 100% efficiency, or a number of different examples here, up to 16 or 32 cores if I wanted. And this will be a very small simulation. You would not use a lot of CPUs for this. But if you run a big nonlinear code, you maybe want to use 512, 1024, a large number of cores. You want to check to make sure that that you'll be utilizing that efficiently. So now, once we've done our test of gyro, we're going to move on to execute the simulation. Okay, this is the execute tab. There's a couple of different ways you can start gyro. Because it can run very, very big, expensive simulations, very often it's run for a certain amount of time, and you look at the output, and then you restart it, and it will continue. It'll continue, many, many times. You might restart it, 10, 15, 20 times even, to get it to the answer that you want. Not the answer that you want, but to get it
the convergence you want.
To the convergence that you want, not the answer. That's a whole other tutorial. So it has these start and restart modes, such as new or continue, or things like retry, or you can reinitialize at t = 0 in the middle of a simulation. If you're going to run through a linear phase and then branch off and do a bunch of parameter scans, you want it to wait for it to go through the linear phase every single time. It's called initialize. So then you have to tell it the number of MPI processes that you want to use. I'm running at PPPL, and there's a couple of different computing clusters here. There's Ellis and Dawson and Kruskal. And so I'm just going to use 4 cores for this example. But if I were to run on, for example, Dawson, it's a minimum of 16 cores. So it has to be multiples of 16, so 16, 32, 64, etc. With any batch submission, you should tell it the amount of time you think it's going to take for it to execute that job. So I give it 30 minutes. It's not going to take nearly that long. And then now here's your submission preference. And this is something that will be appreciated for people that do large simulations versus small, little short linear runs, which is that either you can submit the job and monitor, and OMFIT will query the queuing system and say, is my job done yet? No. Is my job done yet? No. As soon as the job is done, it'll pull all the information back into OMFIT. Now, if, for example, your run's going to take 12 hours and you want to close your computer, maybe what you want to do is submit and store the job ID. And if you submit and store the job ID, it'll submit the job to the queue and store the job information, but it won't sit there with a status bar, waiting and waiting and waiting and waiting. Then you can close OMFIT and go do something else. And then in a couple hours later, come back and open your project and pull the data back.
So if you had more than one job you wanted to submit, do you do that with this?
Yes.
Or, okay.
Yeah, say you wanted to submit 4 different jobs, you would just submit all 4 in turn.
So then how would and then you just
you would change the simulation.
Yeah, you change the label of the simulation and you submit the run. And then I'll go through this. So maybe if I walk through it, you'll see. So let's see, I think I have. Yeah, my run database right now is currently empty. So what I'm going to do is I'm going to submit and monitor the job. Okay, so run gyro is sim1 and wait, it says. I'll move this out of the way. You can see it says running remotely. Let's run gyro. It logged into some worker node on Princeton. It submitted a batch job. And then now my simulation's done. It was fast. All right. So I can now check out.gyro.run. It gives you some information on the current numbers for explicit time advance. It says green, the current numbers are less than 1, good. It probably didn't blow up. And the status at the end of out.gyro.run is that it's converged. So let's say we wanted to submit the job and we don't want to wait. So what I'm going to do is I'm going to delete this run from the run database just to demo this. So I'm going to say submit and store the job ID. So now it says submit gyro as sim1 to queue. And so here it submits it and it stops. And if I check in the queue, I see my job is there, it's running. 9 seconds, and it's done. So what happened? On my run database, the only thing that I have there is what's called job run. It says, here's the job number for my username at this computer. But I don't have any data here. It's up to me to know that my job is finished. And now I say downsync in progress or completed run sim1. As soon as I click that,
when did that button appear? Because it wasn't there originally.
It appears right after you submit it. Okay. It checks if a job is here. And so now I can go and plot my run. Maybe it's only partway completed. I can go and look at it in the middle of its run. Because now linear runs take hours and hours and hours. You want to be able to check it. Now, if I change the simulation to Sim2, I could go submit another run. And then in my run database, I would have 5 or 6 simulations that all just have the job ID. And I would go up here and I would say, I would say Sim1, and then I would say downsync, plot it. Then go back to Sim2. Okay, downsync this one and plot it. And that's how you can run many different simulations all simultaneously.
This is really nice because I've run into this problem in TGYRO where I've
You're
had
waiting.
well, because I'm looking at bold plotting. I've
Yeah.
won, and then then there's a failure when it gets the job ID back. So it would be nice if we could maybe transfer some of this to there.
There's been some nice lessons learned in terms of managing HPC type applications with this module.
So so you said even if the job's in progress, you can like plot like what it's doing. So,
Yes.
But I noticed is that not an option then when you do sit and wait?
Yes, correct.
Okay.
Usually when you're waiting,
You know it's
well,
short.
actually you can do it. You can go to the script and tell it to downsync the run and then go and plot it.
Okay.
But it is not accessible through the graphical.
Okay.
Not easy.
That's just wondering.
So then once a run is done, there's a number of plotting options here. So this is the plot tab of Gyro. Either you can run the command line version of GyroPlot, which comes with the installation of GA code. It's a bunch of plotting scripts there managed by Jeff Candy and Emily Bellet over here in Theory. There's also a series of plots that visualize the data that is stored in OMFIT in a different manner. So if I look here in Gyro outputs Gyro, this is a directory of a Gyro run, and it has a lot of information here. It has the batch submission. It has like the frequency information in terms of the growth rate and the value of omega. So for example, you can just click return on this and it'll plot it. So this is the frequency at wave number KYF3. And you can see here's the growth rate gamma. There's a lot of other information that would be in the directory of that simulation. So here if I say OMFIT plots, I want to plot the frequency and growth rate, it just makes those 2 plots that I already showed you. And so this says your simulation Sim1, x-axis is time, this is frequency, and this is growth rate. You can also plot the ballooning space representation of the eigenmode. And so here's the real and imaginary part of the electrostatic potential. And then you can zoom in and resize these images however you want. Right? You can see the radial extent of the eigenmode. Right? It's a ballooning mode. Peak at theta equals 0. And it shows here the wave number of that simulation. So that's great, right? We've done one gyro simulation. Now let's say we want to do some more gyro simulations. One of the things that's very common for people to do with a gyrokinetic stability analysis is to look at what we call the wave number spectrum. What is the spectrum of modes that are unstable in this x coordinate of k theta rho s? So one example of that I can show here is from a recent paper by Chris Holland, where he did many gyro linear runs to look at the linear growth rate spectrum of low K ITG type modes and high K ETG type modes. And each one of these little points is a gyro simulation, just like the one we just ran. People typically are not going to be publishing this plot for a gyro run. It's simply up to the physicist to say that your simulation is well converged and well behaved. Right? But usually what you do is you have many of these simulations and you consolidate it down into a spectrum of converged runs. And so we're going to show first how you would do that by hand and then in the gyroscan module. So let's say we want to run another gyro case. Well, the best way to do it is to change the name of the gyro run. So I'm going to call this Sim2. Now in reality, people typically come up with their own naming conventions like you would for a directory, which would be, linear, electrostatic, pure plasma, no rotation, all these different things, these long strings with underscores. So this is effectively where it becomes freeform. You name this something that is meaningful to you. So now we're going to change something. So in this gyro run, what we're going to go to is input gyro. You start with whatever you had before. When you change the simulation run ID, it keeps all the settings that you had on the last one. So now you can just change whatever you need to change.
If you change it to something new, then it keeps whatever was there.
Correct.
If you change it to one that was existing, it reloads what was existing.
Right. So I'll show that in a second. All right. And also, if you switch from gyro to CGYRO, it actually wipes out the inputs because the input file is different. So what I'm going to do is now I'm going to change this, and I'm going to change the linear, the single mode wave number from 0.3 to 0.4. And it turns out that to make this run, I need to actually reduce the time step slightly. So I'm reducing the time step from 0.1 to 0.05, but since I'm outputting every 1 A over CS, it still is outputting 100 time slices. Otherwise, if you were to cut the time step in half, but it still output every 5 time slices, you'd have many more outputs. And so just like before, I'm going to submit and monitor this run. So I'm going to say run gyro as sim2 and wait. And I can go back over here and look in the queue, and I can see that my job has been submitted and is running.
Is there a reason you're running this at Princeton and not on Iris? Is Iris slower, for example?
No, well, just because I'm going to submit, in a second you're going to see me submit many runs in parallel, and I don't know how busy Iris is right now. I know that there's always plenty of cores at Princeton for me to do this, but it'll function the same on either one. These are all Slurm submissions, and so the job manager is really good at putting you in the queue and letting you wait. And OMFIT's really good at waiting for jobs to finish. So there's really no issue here. So I'm going to go over here and I'm going to make the same plot that I made before, plot the frequency and the growth rate. Right, so here now it says K theta rho is 0.4 in the legend. I should have also clicked this button here, checkout.gyro.run, status converged. Good. So one thing you might have noticed, I didn't point it out, but as soon as there's more than one run in the database, so here's my run database, sim1 and sim2, this tab will automatically appear. It's called compare. So one of the things we always want to do with OMFIT is to make it so that the standalone codes are able to be compared across many runs. One linear gyro simulation by itself might not be worth a whole lot. It's worth a lot more in the context of many other runs. So here is the standard two-sided list editor, which has all the available runs on the left, and the runs I'm going to plot are on the right. And so there's none right now, but I'm going to click this button that says add all to the right. So now any comparison I do is going to compare these two simulations. So one of the first things you can do is compare the input files. And so it'll say here, the one variable that's different is time step, and time skip and ly. So for sim1 and sim2, I've changed the time step. Time skip was changed automatically because I'm outputting on 1 A over CS. And ly, which is the wave number, changed from 0.3 to 0.4. So it gives you a summary of all the things that have changed in case you forgot. We encourage people to take detailed notes about what you're doing, so that way you remember. We even provide a template for you to fill out as you do this. But this is always just a convenient thing for you to compare. So now we're going to compare the frequency. And so here's two different runs. The blue one is K theta rho s of 0.3, and the green one is K theta rho s of 0.4. See, the growth rates are fairly similar. The frequencies are somewhat more different. As you go up in wave number, the frequency is also increasing more and more and more. All right, so that's how you compare two different runs. You can also compare the ballooning space here. So this is the eigenmode of these two different runs. If you're interested in looking at the width of the eigenfunction, for example, you see that the higher wave number is more narrow. All right, so what I just showed is that you can construct a series of gyro simulations, modifying the input file and renaming them as you see fit to produce many simulations varying one parameter, and then overplotting their convergence and their time histories. But for example, here I scanned wave number. Let's say I scanned the ion temperature gradient. or I scanned something like the plasma elongation, or I had many different radii. And you want to compare them, and you want to compare the converged results as a function of that parameter that you scanned, not necessarily just looking at a bunch of convergence plots, where in your mind you have to now plot as a function of what is being scanned. So hence comes the gyro scan module and the motivation therein. So the gyro module is really great for doing things like orchestrating a nonlinear simulation, which may take a long time. Maybe you want to do one simulation, 2 or 3 simulations. But if you're going to do wave number spectra or large 2-dimensional scans to look at the linear stability as you vary ion temperature and electron temperature gradients, you don't want to go through this every time and have to type in all these numbers. We can easily script and automate the submission of 1D and 2D scans and also their visualization. So that's what the second part of this is. So I'm going to import a module. It's called GYROScan. Here it is, GYROScan. I also want to emphasize that what I just showed for a regression case is identical to what you do for an experimental case, but you just need to first load the experimental profiles in there, as we've shown in the past with the TGYRO and the TGLF scans in other tutorials. So really the graphical interface and the workflow is identical for both of them.
Usually the runs don't take always 10 seconds, right? Sometimes.
Right. So that was a adiabatic electron, pure plasma, collisionless linear gyro run. It's not really physically meaningful. It's for theoretical studies. It's also very strongly driven, which means that it will converge to the dominantly unstable mode very quickly. If you look at an H mode condition, where the gradients are very near marginal, you may have to run for a couple hundred A/CS with collisions. And in that case, you would use 16 cores, and it could take 20 to 30 minutes for that run to converge. You may also take small time steps. That's beyond the scope of what this tutorial is. That's something for you to speak to an expert about in terms of assessing whether or not your run is conversion meaningful. This is more about minimizing the barrier to entry and making powerful tools like this that produce publication quality, cutting edge results more accessible to the broader scientific community. Okay, so when I import the GYROScan module, what you're going to see is that inside GYROScan is the gyro module. If you've understood everything that I've done so far, just think about putting a script, that runs that module, and then collects the output and puts it in a sensible spot. That's what GYROScan does. So I will move quickly through the setup for this case. So when you open GYROScan, the first thing it says is you don't have an input gyro file. So how do you want to create it? This is identical to the gyro module. That's all it says. Really, the code is, if there's no input file, show the gyro GUI. And so here we're going to run the exact same case, input only in regression. We're going to run Regio1. We're going to run gyro. We're going to say set up the regression case. And we've set it up. Now, if I block out the top of this module here, you will see that below this line, you are looking exactly at the gyro GUI. So if I open the gyro GUI, which is underneath it, you will see that this is exactly the same thing. And when I change this, I'm really changing it over here as well. So like I said before, we're going to set up our gyro run. You start with input regression. We've set up our regression case. We're going to look at input.gyro. There's radius, time step as before. And just to get this to run, I'm going to reduce the time step slightly. And just to make it similar, I'm going to output the data every A/CS. And that's every 1/CS. We'll output 100 time steps. The box is set here, which is the normal case. The resolution, the physics, and the output are all the same. It does even show the execute tab, but we're not going to execute here. All we're setting here is that it's a new run, the number of NPI cores, where we're going to run it, and the amount of time that we're allowing it to run. Then you don't run gyro there. You actually move on to the scan tab. Under the scan tab, after you've done a number of scans, you can restore some of the scan inputs if you'd like. But really, the scan is either a one-dimensional or a two-dimensional scan, where you can vary things like temperature and density gradients in a 2D grid. Or maybe you want to look at the wave number spectrum as a function of the electron beta, close to a KBM limit or something. Or maybe you want to just do a numerical convergence test, and you're not scanning plasma parameters, you're scanning numerical resolution parameters. It's totally freeform. So for each simulation, so what I would call this is I would call this scan identifier is GA standard case for Rego 1. The first scan I'm going to do is a wave number scan. Commonly, we call this KY or K theta rho S. The number of variables I'm going to scan is 1. Although I can scan two variables what I call co-linearly. For example, if you have two different ions, you will want to scan their ion temperature gradients together. So you want to scan two parameters at once in a 1D scan. That's different from a 2D scan. So for this example, I'm just going to scan along one dimension. The scanned variable, you can see this red text. It says not all variables for DIM1 exist in input.gyro. That's because I haven't provided a variable yet. The variable I'm going to apply is ly. And ly does exist. Ly is the input variable for K theta rho S. And now what about the values? The values I'm going to scan, I'm going to use a Python function here and say set the values. I'm going to scan K theta rho S from 0.1, 0.2, 0.3, 0.4, 5, 6, 0.7. Now I just happen to know that that's the range of the low K ITG modes for this case, just because this will converge well because I tested it 15 minutes ago. But this could be any number of things. So this is 0.1, 2, 3, 4, 5, 6, 7. This would be a crude low K wave number scan, very similar to what's done here. This was done from K theta rho S of 0.1 to 1 in 0.05. But we're going to do a core scan just for demonstration purposes. So now when you run gyro, there's a couple of ways to do a gyro scan. You can do it sequentially, which will take time. And it's kind of a debugging mode, really. So it says sequential debug. Then there can be parallel batch, which is similar to run and don't wait. Just submit it to the queue and go do something else. Or there's also parallel wait. And so for this example, I'm going to do parallel wait. There's a couple of options. You can resubmit converged runs if you want. For example, if a run is converged but you want to reduce the tolerance, you can resubmit it. But normally you don't need to submit converged runs, it's defaulted off. So now you can test all these gyro runs in parallel, and it will run gyro-t, it'll produce an output file, and you can check all those to make sure that all your settings are appropriate. Or for this example, I'm just going to run it. Normally you would want to test it, and then you would check it. But for this example, I'm just going to run. So I'm going to parallel run a gyro scan. I'm scanning one variable from 0.1 to 0.7 in steps of 0.1. And so I submit this job, and if I go over here to my terminal, I see I have all these different simulations that are running. Each one is using 4 cores. They've only been running for a few seconds. But I'm waiting for these jobs to finish. So now these will turn green as the various simulations finish. They'll either hit the maximum time limit, or they've hit their convergence requirement, and gyro says, okay, it's done. The simulation can be stopped.
When you say the maximum time limit, you mean the wall time? Or?
Yeah, the wall time. So gyro regularly writes restart files. So maybe I say I'm going to run it for 500 over CS, but on my computing cluster, I only can run for 12 hours at a time. Maybe it only makes it to 80, but that's okay. the queuing system will stop the run, and you can go back and restart it here if you want.
So when you say the convergence criteria, I noticed I don't think we didn't set that at any point, do we? I assume it's kind of complicated for a code like this. So that
Well,
should be more
linearly, it's not too complicated.
It was on the time, the number of time steps on the decimal part of that.
Yeah, the decimal
Oh,
part of the
that's
time
correct,
step is
that's
the convergence. Now, non-linearly, there's no real convergence metric. You have to look at the statistics of the simulation. So that took a little longer than I expected it to, but that's okay. So now I have a whole bunch of gyro runs that you can see over here. It says step 2 of 7, step 6 of 7. It submitted them in some order. So now I can check the gyro scan, out.gyro.run. And I say, oh, okay. Most of my simulations that I see here, KY1, KY2, et cetera, are all converged. Oh, this one, number 7, unconverged. So just to make sure everyone knows where it goes into outputs, GA standard case, 1D scan, and it's KY 1, 2, 3, 4, 5, 6, 7. It's just the number in the list. And so now I can go over here to plot. I'm going to plot a scan. My plot dimensions can either be 1D or 2D. If you have simulations that have already been done, you don't have to type in this information. The OMFIT automatically searches this tree structure for simulations that exist, and you can load the defaults for a given run. Okay. So the label for that run is KY. The independent variable that we scanned was LY. And so now I can go down here and compare the frequency. So when I make this plot, I get the convergence plot, which is the same that I had before, right, on the compare tab in the gyro GUI, but now there's an extra tab under scan results. So here's the convergence. You should look to see that all these make sense, and one of them you see is not converged. And then you have the scan results here, which is the wave number spectrum. So this is the growth rate as a function of the x-coordinate Ly. And then this is the frequency. And in gyro, the sign convention is that a negative frequency mode is an ion-directed mode. So this is likely an ion temperature gradient-driven case. There's a couple of dashed lines here. One of them is the diamagnetic drift frequency, and one of them is the magnetic drift frequency, omega star and omega d. And so you can see here that this mode is, as is typical, it's somewhere between these two limiting frequencies. This often helps in identifying, from a textbook standpoint, what the linear instability is. It's an ITG mode. It's near this frequency. Maybe it's above the E cross B shearing rate or very close to it. This also shows E cross B shear here, but E cross B shear will only actually exist if you first of all type it in a theoretical case, or if it's an experimental case and you have an E cross B shear profile, it'll put a horizontal line here that'll show you the E cross B shearing rate. So if I go back to this example from Chris Holland, here's the linear growth rate. You see this broad low K spectrum. You have an E cross B shearing rate, and you have these modes that are above the E cross B shearing rate. So if you have an E cross B shearing rate in the simulation that you've done, it would show up here as a horizontal dashed line. All right, so just as another example, if I delete all these cases, I'm going to delete all these runs. I'll go back to scan, and just for an example, I'm going to say parallel batch. I'm going to go back here and I'm going to say parallel run gyro scan. So here, rather than waiting, you see that it's doing them somewhat sequentially here. Maybe it's just the communication with the nodes. But here now I could go home, right? And I could quit OMFIT. Because what it's done now, I can just show you here in the queue that all my runs are here in the queue and they're running again. That in my run database, I've stored the job run ID and the inputs and the settings. There's no outputs. But if I save OMFIT, I can quit the application. The entire, this node that I'm working on can, go down for maintenance. Right? I can reopen OMFIT, and so long as I have the jobs that are running, so as long as I have the job run, the ID here, I can just go back and say downsync the gyro scan. So here, when you do it in batch mode, you can also say try to downsync running jobs. So let me see if this. So I'm going to try to downsync gyro running jobs. And I click this button, downsync gyro scan GAC intercase. And you're going to see over here in the terminal it says job 5 still running, job 6 still running. Job 7 appears complete. So then it'll print off a summary here. 0 simulations are pending. They've also at least started. 6 simulations are running. 6 simulations are running and downsynced. 1 simulation is completed and downsynced. There were no errors. I can go over here and plot and compare my frequencies and see that, you know, one of the runs has made it fairly far. The other runs haven't quite converged, but they're close. So if I go and check the queue, I see they're all done. I can go back here to the scan and say downsync. Now it'll say job appears complete, downsyncing. Job appears complete, downsyncing. So for an experimental case, if I'm doing a complete wave number spectrum, like what Chris did here, where you have 10 or 20 modes in the low K and 40 or 50 modes in the high K, you know, you don't want to check each one individually. You want a means of summarizing. And so now here I can check my gyro scan, out.gyro.run, and you get the same answers you had before. I just repeated those simulations. Go back here and plot and compare now. You can see the different runs took a different amount of time to converge. Now, we have about 10 minutes left. And so what I'm going to show now is, okay, one of those runs did not converge. So what do? You have a couple of options here. You can go over here to gyro, and under execution, I can say continue. And now when I go over here to run gyro, I can run these jobs in parallel, and the ones that did not converge will be resubmitted. Any jobs that were converged will not be resubmitted. So that's why you have a button here that says you can submit converge runs. So just to go through this, if I say new, and I go to scan, and I say parallel run gyro scan, it'll say gyro already run, not continuing skipping. You know, for each one, no runs to do. Either all are done or no restarts. This keeps you from doing things where you click a button and, man, you just resubmitted a bunch of things that took a couple of hours and now you're shooting yourself in the foot. Because once it restarts, it really restarted. It deleted the output. So now if I go to gyro and I say I want to continue, and I go back to my scan, I'm just going to run this way. I say parallel run the gyro scan. Oh, I thought that it should have done that. If I say converge, submit converge runs, what'll happen is that the ones that have already converged will finish very, very quickly. And the ones that have not converged will take a little bit longer to run. I hope I set that right. Yeah, continue. Yeah, so a bunch of the ones that were set to continue, they were already converged. And so they will take almost no time to finish. But that one simulation, KY7, was not converged. And so it'll take a little bit longer for that one to finish. Now, one of the things that you may want to do is you may want to pull an individual gyro run out of the scan. Say as you go up in wave number, maybe you say, oh, well, you know, I'm getting into the electron scale. Maybe I should run with gyrokinetic ions and electrons. And so one thing that you can do here, if this thing finishes, is once you've done a gyro scan and you've looked at the outputs, maybe, for example, gyrokinetic simulation number 6, I want to look at it individually. Maybe I want to change some of the settings. I can hit copy and paste here and return. I can load this gyro run into standalone gyro. Now, I have just loaded this simulation into the underlying gyro standalone GUI. I can go in and I can change the time step. I can change the resolution. I can plot this individual run, which you can see here. K theta rho S of 0.6. This is the run. I can then go and do something different with the simulation. I can increase the radial resolution, get it to better convergence. And then once I'm done with it, I click on this button here that says Update Run in the gyroscan outputs. So then I click this button, and the gyro inputs and outputs from the standalone module that are here get put back in their rightful place in the scan. And then when I go and plot the scan, and I compare the frequency, whatever work I needed to do to get that run to a level of convergence I was satisfied with, it'll appear with all the other ones. And so you see here the scan results here. So this run out here in the end is still not quite converged. Maybe I did go there and intervene and fix that one run without starting from zero again. So it allows you to do one of these things, which is like going into a directory and say, I'm going to change a setting and rerun this, and then I'm going to go do my plotting script. So that shows, as an example, how OMFIT can orchestrate many different gyro simulations, run them in parallel, collect the outputs, and then provide visualizations for multiple different simulations. It also has utilities for parsing the outputs, checking to make sure they're converged, to kind of sanity check all the different runs. So everything that I showed you here from a theoretical use case can also be done for any experimental condition. And you can even go beyond this and do nonlinear simulations. And so here I have an example of a nonlinear simulation from the case that we were running the GYRO tutorial on, which is a D3D reference shot, just to show you what the output looks like from a nonlinear gyro run. So here I have a nonlinear gyro simulation. My run ID is gyro nonlinear D3D ion scale. It's at radius rho 0.7, 16 toroidal modes, and it's my second attempt at this run. You see here all the experimental parameters that were used for this. I used, when you do an experimental case, it asks you to choose a template. And so all the templates are listed here. And you would just say load the input.gyro template. And then you go to input.gyro, which is the same as I showed before, only now for the radial coordinate, you have these options of rho, radius, or sine normal. So when I type in rho 0.7, it'll tell me what the gyro R over A value is for that. Everything else is kind of the same. Only you have things like the nonlinear multiple modes in terms of people that know gyro know these variables, which is the box multiplier and all these outputs, the resolution, the physics, the output, et cetera, et cetera. Execution, I was continuing this run on Dawson at Princeton with 256 cores, and I would run it in 10-hour blocks. So I would say, run gyro and wait, or run and monitor. Once you have a nonlinear run, you can go in here and plot, for example, the time summary. So here's a nonlinear gyro simulation for a D3D reference shot. And you see how long it's run. It's run for close to 1,000 CS over A. It's gone through a very long electron dominated phase. The ion modes finally start to come up after 500 time units with a big linear growth, and then it saturates here into a bubbling nonlinear phase. And here it outputs things like, when I set my time averaging, it'll output the value for the ion and electron energy fluxes and gyro bone normalized units. At the top, you see these are the turbulent potentials and the n=0 zonal flows that are oscillating in time. And then it provides also a summary of the spectrum. So you can see here as the simulation went along in time, this is time on the x-axis and wave number k theta rho s on the y-axis. This is the particle flux, the energy flux, where you see which mode really blew up before it turned into becoming broadband turbulence. It was around k theta rho s of 0.5. And then it has the average spectra in terms of particles. Here where you see a low-K outward ITG transport, and some inward electron type pinch as you get to the TEM scales. This is the energy flux spectrum. You see here is the low-K ion modes, and here's the electron modes where you start to get electron transport at intermediate K. And then at the right is essentially the time averages. And so you can then also compare multiple gyro runs. So here I have a list of nonlinear simulations with various options, and you can see what your choices on the input parameters and the impact they had. You can compare a gyro run and a CGYRO run. It's quite full featured, and so this is the current status of this tool for doing these studies. And so this is something I've been using quite extensively lately, and so I have a number of people. So in conclusion, we're just about out of time. The gyro module is very powerful for doing individual gyro runs, linear and non-linearly. If you're doing a scan and you don't want to deal with the tedium of typing so much, you can use the gyro scan module to scan over parameters, and there are built-in visualizations that allow you to plot things across your 1D and 2D scans. If you want to then be more ambitious and start doing scans of nonlinear runs, then you would do something along the lines of what, say, Chris Holland showed in this plot, where each one of these points is a large nonlinear gyro simulation, and here he scanned the E cross P shearing rate. And so the gyro scan module also allows you to do these scans, although you should think long and hard before launching 20 nonlinear simulations that each use thousands of processors. But you are not restricted from doing that. We encourage people to come and look at the gyro tutorial, add your comments, questions. There's quite a bit of information in here, including a section at the bottom for identifying instabilities. So if you are doing linear gyro runs, what does the ballooning mode structure look like? And what are some of the sensitivities that mode have, both electrostatic and electromagnetic? So kind of a knowledge base here for doing ITG and ETG and trapped electron modes and kinetic ballooning modes. A couple of examples around theoretical use cases. So with that, I thank everyone for attending this tutorial, and I hope this was useful.
That was great.
Thank you.
Thanks.